Hello, everyone. Questions? By the way. There's a snowstorm on the horizon. It's been snowing all day. Heavy winds, but not as cold as it's been. Good afternoon, everyone. Questions while we wait another minute or two for people to come in? That's right. Questions, anybody? No? Let's do one more example of what we were working on last time, and I'll show you how you can verify that the answer you have is correct. Consider the following scenario where you have a two-sector economy consisting of agriculture and manufacturing. To produce 1 unit of agriculture requires 0.8 units of agriculture and 0.2 units of manufacturing, and to produce 1 unit of manufacturing requires 0.2 units of agriculture and let's say 0.7 units of manufacturing. How many units of each must be produced to meet a demand of 2 units of agriculture and 3 units of manufacturing. Good afternoon, everyone. For those of you just joining us, I wanted to do one more example of what we were doing last time and show you how you can check your answer. So consider the following scenario. So let's say we produce, let X and Y be the production of agriculture and manufacturing. Let's not use this terrible notation here. Let X be the unit of agriculture produced and Y be manufacturing produced. And you know the deal, right? The amount of units we produce minus the internal consumption, right? If this is agriculture and manufacturing, right? The Leontief input-output matrix, in order to produce 1 unit of agriculture, requires 0.8 units of agriculture and 0.2 units of manufacturing, and similarly, to produce 1 unit of manufacturing, 0.2 and 0.7. This should meet our demand of 2 units of agriculture and 3 units of manufacturing. And you know what to do, right? This is, if we denote this matrix by, let's say, capital A, I minus A times XY should be our demand. And consequently, XY should be I minus A inverse times 2, 3. I minus A, let's do that here, is easily seen to be 0.2 minus 0.2 and 0.3. That's I minus A, so the inverse of that. We can use the shortcut because it is 2 by 2. AD minus BC, so 0.06 minus 0.04, that is 0.06 minus 0.04, that's 1 over 0.02. Interchange these two, and negative of those two. So we have that. And what is that? That is 30 over 2, so that's 15, 10, 10, and 10. So this is 15, 10, 10, 10 times 2, 3. 30 plus 30 is 60. And 20 plus 30 is 50. Now, here's the question. Is this correct? Is this the right answer? So X is 30, X is 60, Y is 50. Let's verify if this is right. The production of 1 unit of agriculture requires 0.8 units of agriculture and 0.2 units of manufacturing. So if you're producing 60 units of agriculture, you are eating up 60 times 0.8 units of agriculture and 60 times 0.2 units of manufacturing. And if you're producing 50 units of manufacturing, this eats up 50 times 0.2 units of agriculture and 50 times 0.7 units of manufacturing. So let's put all of that together. So how much agriculture is consumed? This is 6 times 8 is 48. So that's 48 right there. So consumed 48 units of A and 12 units of M, as well as 10 units of A and 35 units of M. So in total, how much is consumed? 58 units of agriculture and 47 units of manufacturing. You produced 60, you consumed 58, so you're left with 2. You produced 50 units of manufacturing, you consumed 47, you're left with 3. Exactly as expected. How are we doing? Convinced? Questions? Now, what we've been looking at, this scenario here, is known as the open model. You are able, you have a production surplus that allows you to meet a demand. You can imagine an island nation or a closed nation where you don't want to export anything. You just want to produce as much as you're going to consume. Imagine a model where nothing is left over. Everything is consumed in the production process. This is known as a closed model. Imagine a scenario where everything is consumed in the production process. Nothing is left over to meet an external demand. So that cannot be the question. Rather, the question becomes, what ratio? What is the ratio of goods that need to be produced? Right? If all is consumed in the production process, right? If A is the internal consumption matrix, then everything that is produced is eaten up, right? Or if you bring this to the other side, we have this. Now, if I minus A is invertible, then we're in trouble, right? And nothing can be produced. So what happens in the closed model is that I minus A is actually not invertible. When does that happen? How can you tell if we have a closed model or open one? In the closed model, all the columns independently add to 1. Let's take an example. Consider a two-sector economy depending on yams and pigs. As you know, the yams is the power that be. And suppose that to produce 1 unit of yams requires a quarter of a unit of yams and 3/4 of a unit of pigs. Similarly, to produce 1 unit of pigs requires half a unit of yams and half a unit of pigs. Here's the question. What is the ratio of yams to pigs that must be produced? First of all, let's write down the internal consumption matrix. If we call that matrix A. To produce 1 unit of yams requires a quarter of a unit of yams and 3/4 of a unit of pigs. Similarly, to produce 1 unit of pigs requires half a unit of yams and half a unit of pigs. So you see what happens, right? Each of the columns here adds to 1. 3/4 plus 1/4 is 1. Half plus a half is 1 as well. So we are now in the presence of a closed model. And if we look, right, so I mean, in this case, what are we asking for? We are asking for what is the ratio? So here's the question, what is the ratio yams to pigs. Right, so this is what we're solving. Or equivalently, as we pointed out, I minus a times x equal to 0. So what is I minus a? Right, the identity times this. Can we do that in our heads? 3/4 minus a half minus 3/4 and positive 1/2. Right, so there it is. What are we looking for? We're looking for the values of x and y, right? Which make this equal to 0. But what is that? This is 3/4 x minus 1/2 y and minus 3/4 x plus 1/2 y. So we're asking, when is this equal to 0? Well, this gives rise to a system of equations, right? First entry must be equal to the first entry. And second entry must be equal to the second entry. We have a system of equations which we can solve by putting everything into a matrix and row reducing. What matrix do we get? We'll reserve the first column for the x's, second column for the y's, third column for the constants. There it is. Exactly, Annie, as Annie suggests, the two equations are essentially the same. And notice that this matrix here on the left is actually I minus a. So you're really just augmenting I minus a by a column of zeros. And as you can well imagine, whatever row operations you do, right, in this case, row 2 plus row 1 for row 2, no matter what row operations you do, that column of zeros is not going to change. It's always going to be a column of zeros, right? If you add 0 plus 0, you still get 0. If you multiply 0 by any number, you still get 0. Right, so this column of zeros is always going to be 0. I'm going to drag it along for this example, but in the next example, there's really no point in dragging along a column of zeros, right? I mean, matrices are supposed to be efficient. We'll leave that column of zeros outside with the understanding that it's always there. Let's finish that up. Is this in reduced echelon form? Of course, you know it's not. Let's multiply row 1 by 4/3. And what do we get? There we go. And as Britton suggested, the answer to this will have a parameter. So first of all, we are now in reduced row echelon form. What is the solution? Y does not have a leading one. Y gets replaced with a parameter, t, absolutely. And x is easily seen to be 2/3 t. So question is, what is the ratio of yams to pigs? Right, I mean, we never actually, that was a bit sloppy here. We never actually introduced what the variables were. We should have, well, did we? Maybe we did. Let x be the number of the production of yams and y the production of pigs. I don't remember if we did, but I mean, we should have if we did not. So the production of yams to pigs, 2/3 to 1, or if you let t be 3, we have a ratio of 2/3. For every 2 yams produced, you should produce 3 units of pig. How are we doing? Questions? So this is the answer we're looking for. 2/3, a ratio of goods produced. Let's write up. We'll take another example. Why is I minus A not invertible? It's a good question. It's a good question because it's not immediately obvious. But in this case, I minus A, first of all, observe that the reduced row echelon form is this, which is not the identity. Consequently, your matrix is not invertible. Secondly, since it was 2 by 2, you could have done the shortcut 1 over AD minus BC times the matrix, but AD minus BC would have been 0 here. So 2 reasons why it's not invertible. And it turns out that this is always the case. You can prove that. The proof is beyond us, but you can prove that I minus A is not invertible in the case that the columns add to 1. If all the columns add to 1, I minus A is not invertible. What does the ratio tell us? It tells us that for every 2 units of yams produced, we should produce 3 units of pig. Consider the following question. Suppose that we have a 3-sector economy made up of agriculture, manufacturing, and transportation. Suppose that the production of 1 unit of agriculture requires 1/3 of a unit of A, 1/3 of a unit of manufacturing, and 1/3 of a unit of transportation. Production of 1 unit of manufacturing requires half a unit of agriculture, 1/4 unit of manufacturing, and 1/4 unit of transportation. And finally, 1 unit of transportation requires 0 units of A, 1/4 unit of manufacturing, and 3/4 units of transportation. Find the ratio of the three commodities in the closed model. Now, they specifically tell us that it's a closed model, but of course they did not need to. Right? If we look at the input-output matrix, to output 1 unit of agriculture requires 1/3 of a unit of each. To output 1 unit of manufacturing requires 1/2 a unit of agriculture, 1/4 and 1/4 of manufacturing and transportation. And finally, to output 1 unit of transportation requires 0 agriculture, 1/4 of a unit of manufacturing, and 3/4 of a unit of transportation. Observe that this adds to 1, this adds to 1, and so does this. So right away, we're guaranteed that this is a closed model. Let's go ahead and introduce some variables. Let X be the units of agriculture produced. Y are going to be the units of manufacturing produced, and Z is going to be the units of transportation produced. The question is, what is the ratio of each that need to be produced, right? In other words, this, let's call this big matrix A here. So A times X, Y, Z. Right? So how much is consumed in the process should be equal to how much is produced. Or, once again, we have this. So we saw that you augment I minus A by a column of zeros. Of course, there's really no point in doing that. So right, I mean, if you augment this by a column of zeros, that column of zeros is always there. Really no point in doing that. We want to be efficient. All right. Whatever you want to do, what do you want to do? I feel that we might use this one to clear that one out. Row 2 minus row 3 for row 2. And then maybe do row 2 minus row 1 for row 2. Sorry. This should have been row 3 minus row 2. For row 3, and then row 2 minus row 1 for row 2. Maybe, I don't know. Do I want to do anything else? Let's leave it as that. I'm going to stop writing that column of zeros now. Aren't we doing I minus A? Oh, yeah, sorry, jeez. Good catch, because this was going to be terrible. Thank you. Thank you, thank you, thank you. I went way too fast. Way too fast. Thank you for that. This is my A, not my I minus A. Absolutely. Thank you. So what is I minus A? Can we do that in our heads? 2/3 minus 1/2, 0. And again, right, so let's start this over. You augment by the column of zeros. Thank you everyone for stopping me. You augment by the column of zeros, but yeah, so now not as nice. What do we want to do? Do we want to get rid of the fractions? I mean, I'm always tempted to get rid of the fractions. You don't have to, but it seems like the thing to do, does it? Let's say 1/2. Row 1 for row 1. Let's try leaving the fractions in, see what happens. I am, however, going to stop writing this column of zeros with the understanding that it's always there. So let me use this 1/3 to clear out the column. Row 2 plus row 1 for row 2. Row 3 plus row 1 for row 3. So this plus this plus this, that's going to be a 1/2. This plus this plus this, that's a minus 1/2. All right, let's use this 1/2 to get rid of that. So row 3 plus row 2 for row 3. And then maybe use this 1/2 to get rid of that. Row 1 plus 1/2, row 2 for row 1. So 1/3, 0, right? This plus 1/2. This plus 1/2 is minus 1/8. 0, 1/2 minus 1/4. and 0, 0, 0. Finally, let's get rid of the fractions here to bring it into reduced row echelon form. 3 row 1 for row 1, 2 row 2 for row 2. And now this is where we recall that we actually had a column of zeros here that we never bothered writing down, but I mean it follows us throughout. And this is in reduced row echelon form, so we should be able to read off the solution. What is the solution? Well, z does not have a leading line, so z gets replaced with a parameter. This first equation is telling us that 1 minus 3 over 8 1x minus 3 over 8 z is equal to 0, or x is equal to 3 over 8 z, but z is t, and similarly y is 1/2 t. Absolutely. So we're looking for the ratio of goods to be produced. And it's nice to get rid of fractions. If you take t to be 8, for every 8 units of transportation that you produce, you'll produce 4 units of manufacturing and 3 units of agriculture. The ratio of goods produced, 3 to 4 to 8. How are we doing here? Questions? Anybody? So please don't make the same mistake I made, right? It's I minus A. Where does the 4 come from? If I take t to be 8, all the fractions disappear, right? If t is 8, 8 over 2 is 4. How to find the ratio? I mean, really any value of t will give you a ratio, right? Any non-zero value of t. So if t is 1, you'd have 3 over 8 to 1/2 to 1. That would be an acceptable answer. I mean, it's very nice to get rid of fractions. So if you take t to be 8, you have nice whole numbers. When t is 8, x is 3, y is 4, and z is 8. 3 to 4 to 8. Questions here? How are we doing with the closed model versus open? You should, as I was asking, would the question necessarily tell you that you have a closed model? Or would you have to check? You should not expect the question to absolutely spell it out for you. But you should be able to recognize that you have a closed model. In a closed model, as you know, all the columns add to 1 independently. Another big hint that you're dealing with a closed model In an open model, the question asks you, first of all, the question gives you a demand and asks you how many units of each commodity need to be produced to meet a certain demand. In a closed model, you have no demand because everything is consumed in the production process. And as Britton suggests, if they're asking you for a ratio, that's yet another hint that it really should be a closed model. So even though they might not say flat out, you can read that that's what you're working with. There are many hints leading you to that conclusion. Somebody's asking how to read the ratio. Right? I mean, there's no unique answer to that. Right? I'm suggesting any value of t will work, right? So if t is 16, you could have a ratio of 6 to 8 to 16. This is the same ratio as that. And any non-zero value of t will give you a correct answer, right? If t is 1, 3/8 to 1/2 to 1, I mean, it just doesn't look as good. And, I mean, it's nice to not be working with fractions. So it's customary to take a value, smallest value of t, which gets rid of all the fractions. T equals 8 gives you this nice 3:4 to 8 ratio. So for every 3 units of agriculture, you should produce 4 units of manufacturing and 8 units of transportation. As Ben suggests, if everything is consumed, there is nothing left over to meet a demand. So notice that this question did not give us a demand to be met. Everything is consumed in the process. I would accept any form, but this is really the one I'm looking for. Will the ratio always be positive? The answer is yes. Yes. Right? Because again, this is a physical problem and we don't expect a negative number of units to be produced. So if you get negative somewhere, I would rethink the work. Something must have gone wrong somewhere. Questions? Moving on? Let's move on. What we wish to do now is move on to something known as linear programming. The name seems daunting, This has nothing to do with computer programming. Really, what we want to do is optimize linear functions on closed and bounded sets that are determined by inequalities. So to that aim, we're going to start with a review of graphing inequalities. And you've done these before, but let's just take some time to review this. And let's jump right into it. We are asked to graph let's look at the graph of y less than or equal to x plus 1. We're going to start with the graph of y equals x plus 1. And you know that graph. You know the graph of y equals x plus 1. It's just a straight line. Now, you want the y values which are less than that. So everything, right? I mean, this is the x and this is the y. So we're looking for the y values that are less than that. Everything under this line. There it is. This is the graph of the region y less than or equal to x plus 1. And you can convince yourselves, if you take any point in here, right? I mean, when x is 1, y is 2 here. So this point, the point when x is 1 and y is 3 over 2, this point should be in your region. 3 over 2 is less than or equal to 2, 1 plus 1, right? So 3 over 2 is less than or equal to 2. You know this to be right. This point is in your region. Trivial. Let's try another one. Right, same thing. Let's start by looking at the line y equals x plus x minus 3. And again, I mean, it's just a straight line with y-intercept minus 3 and x-intercept 3. Right, this is the line y equals x plus 3. And we want the region y bigger than or equal to, in other words, everything above all the y values that are larger than this line. This is the region. I know some of you might use a different notation. In other words, some of you might shade the region not included, which kind of does make some sense once in a while, but that's not what I'm doing. So just keep that in mind. What about a strict inequality? right? Not bigger than or equal to, just bigger than. How are we going to distinguish between the two? First of all, why don't we isolate y here? This is the same, bring that over as y bigger than negative 1/4 x plus 6/4. Is everybody comfortable with that? Is everybody with us? Right? These two things mean the same thing. We're going to graph this one here by, first of all, graphing the line y equals minus 1/4 x plus 6/4. So when y is, so right, I mean, we're going to start by looking at the line y equals minus 1/4 x plus 6/4. This is a straight line with y-intercept 6/4. And x-intercept, when x is 6, y is 0. So it goes through these 2 points. I did not want to do that. Thank you, Annie. Right, we're going to distinguish between when the line is included versus when it's not by a dotted line versus a straight line. So the straight line does include, the dotted line does not. Right, so this is the limiting case. This is the line y equals that, but it's not going to be included in our domain. What do we want? We want the y values which are larger than that. So everything up here, not including the dotted line. Two more examples and then we'll move on to combining several of these. Right, y bigger than 5. Well, y equals 5. Again, y equals 5 is this horizontal line, and we want everything above. Let's do one more. X bigger than or equal to -4. Right, so x equals -4, you know what that means. That's a vertical line. And what do we want? We want the x values that are bigger than that. So the x values bigger, everything here. Convinced? Let's now combine several of these to define a domain known as a feasible set. Question is asking us to graph the feasible set feasible set is the set of points which satisfy both of these inequalities. So let's start with the first one. Maybe let's bring the y to that side. Well, we're going to rewrite this in a way that we can deal with. And maybe the second one while we're here. What page is this? 126. So let's start by graphing the first one, y equals 4x minus 6. So y equals 4x minus 6, and that is not going to be a part of it, right? So it's going to be a dotted line. When x is 0, y is negative 6, so it goes through this point right here. And when x is 6 over 4, apparently 6 over 4 was there. There it is. So that's that line. And what do we want? We want the y values, which are bigger than that, right? So everything above. Right, again, some of you may have difficulties with these inequalities. Look at the origin, right? Is the origin part of your domain? If x and y are both 0, you have minus 6 is less than 0. Is that true? Indeed it is. And consequently, the origin is in the domain. Let's graph the other one. The other one, y equals minus 3x plus 9. Y-intercept of 9. X-intercept of 3. Remember that this was 6 over 4. So 3 is bigger than that. So we have this, and what do we want? So again, it's not included, right, because it's a strict inequality. And now we wanted y to be less than that. So the stuff underneath that line and our feasible set is the overlap of the two. Whatever region is doubly shaded, exactly this region right here. This is our feasible set. And so this region right here is our feasible set. Convinced? Relatively straightforward, right? You've seen this. You've seen this kind of stuff before. Same thing, just more inequalities. Nothing to worry about here, right? Let's rewrite these inequalities in a fashion we can deal with more accurately. Let's bring the y, 2y to the other side there. So 3x minus 6 is bigger than or equal to 2y. And let's bring the 2 to the other side by multiplying the whole inequality by 1/2. And when you multiply an inequality by a positive number, you know the inequality is maintained. So this is the same as y less than or equal to 3 over 2x minus 3. If you bring the x to the other side here, this becomes y less than or equal to minus x minus 5. And then you have this third one right there. All right. Let's start with this one. A y-intercept of -3. An x-intercept of 2. And we want the y values less than this, so underneath the line. This is -3, and this is 2. Excellent. Let's look at this next one. When x is 0, y is -5. And when x is -5, y is 0. So there it is. And what do we want? We want the y values underneath that. So that is unfortunate. That is very unfortunate because now I'm restricted to stuff underneath. So I'm already just in here and there's very little room there. So let's redraw that again right here. What did we have? The -3 and the 2. And then the -5 and the -5. So we had this region. And then we have this region. So already we're in this doubly shaded region right here. And then y less than or equal to -6. -6 is right here. So we want the stuff underneath that. So we're in this triply shaded region. This is our feasible set. At some point, it becomes difficult to see what's going on. So, once you've perhaps drawn what you want and have understood what the feasible set is, it's sometimes very nice to rewrite it or redraw it in a nice form for the reader, right? This one here was the line y equals 3 over 2x minus 3. And this one was y equal minus x minus 5. Right, so this is our feasible set that we've understood as being the triple D shaded region over there. But nicer to understand. Indeed. One more? We want to do one more? How are we doing with this? This is, of course, very easy high school stuff. Let's take it a step further and ask the question, are these feasible sets bounded or are they infinite, right? This continues on downwards without bound. This is an unbounded set. A bounded set, you could actually draw a circle around. So this is not bounded, right? This continues on to infinity. Let's look at this. Again, let's rewrite these. Y is less than minus x plus 3. Here, let's interchange. If you multiply the whole thing by 1 over 6, you have y less than or equal to 1/3 x minus 1. Let's graph these. First one, y equals minus x plus 3. Y-intercept at 3, x-intercept at 3, and it's not included, right? And we want the y values less than that, so everything underneath. This is the region again. Convince yourselves. If x and y are both 0, 0 is less than 3, the origin is in your set. Secondly, y less than or equal to this, y-intercept of -1, x-intercept of +3 again. Interesting. So that is included. And what are we looking at here? Less than, again, so everything underneath. Good. And finally, y bigger than or equal to 2. Y equals 2 is right here. Bigger than or equal to 2 is everything up there. And now we want everything that is triply shaded. And of course, you recognize that Exactly, right? The feasible set in this case is empty. There are no values of x and y which satisfy all three inequalities. So there it is. Questions? Anyone? So as I suggested, next time we're going to ask the question, how do we find the maximum and minimum of functions on these feasible sets? We'll see two different methods. And we'll discuss these on Thursday. Thank you all for coming. You guys have a good one, and I will see you then.